Hi guys, today a bit late.
And in the
1 minute. No, VS Code go இது ஓப்பன் பண்ணிக்கிறேன்.
next part, we have the ending index. And this is the next data type that we have. Another concept after that I want to cover is in Go, functions are first class citizens. And by that, I mean there can be anonymous functions also. So here we have a function declaration which does not follow the typical function declaration that we have here. Here we have the func keyword, then we have the name of the function, then the curly braces start. We don't have the same structure here. What you're doing, since functions are first class citizens, you can assign a function to a variable right inside any function. So what we are doing here, we have a variable, we are using the short declaration form, and we are assigning a function to that. What this function does, it takes two parameters, x and y, which are of type float64. It returns the same type, float64, and it actually does this math calculation. It does x into x plus y into y, and it calculates. Calculates the square root of that and returns it. This is what this function does, and we are assigning this function to this variable. Now we can use this will be x, this will be y. First class citizens, you can assign functions, you can assign anonymous functions to variables. Now the second thing, we have a function here. We have a function here which takes another function as a parameter. We can also do that because functions are first class citizens in Go. We are taking a function as input, and what this function's signature is, it takes 2 float 64 and returns 1 float 64. And if you see, this signature matches this signature. We don't have to write the name of the variables here because this is just a signature of the function. Okay, 64 value. So for now, we have this function whose signature matches this. We can pass the hypot, this function, in because we can pass functions into other functions. Go provides another nice feature called closures. Now, if you are a JavaScript developer, you are coming from a JavaScript background, or any other programming language which has the same feature of closure, which I'm not aware of, I'm aware of JavaScript, then you'll get it. It works exactly the same as other languages, the same as JavaScript, the same way closure works in JavaScript. But if you are a beginner and Go is your first programming language, or you are coming from a programming language which does not have the concept closure, then I would say don't take it too seriously. Don't try to understand everything around it. Just know that this nice feature exists and they are used in a lot of places, in a lot of libraries. You might not use it explicitly, that you won't think like, now I'll use closure for this. But closures are used implicitly in a lot of places. So just know the concept that it's there, and it's not a big deal if you don't understand it right away. Now, this is how it works. This is how closures work. We have a function, and this function returns another function. And this function has access to the variable of the outer function. It has access to sum. Now, because of that, even after this function returns, it has access to a state called sum, which it can keep using. And let's use this example to understand how exactly this works. So let's first run this. Okay. We have different iterations. Let's go through that quickly. Now, Go provides a feature called methods, which allows us to assign functions to types, any type. It can be struct, it can be integer, it can be string, any type, any custom type, any, as long as that type is defined in the same package. That is the condition that we have to match to assign methods to a type. Now, we'll typically see types being assigned to structs, but there are also use cases of types being assigned to user-defined types, like custom types that take from integer or strings and arrays and all. Okay. Now, how does it work? How do methods work? Let's first look at the syntax. We have a struct here, which is, and whose name is vertex. It has two fields, both of type float64. Now, in the next line, we are defining a method on the type struct. What it does is, this part is the same as a function declaration. Okay. If we had a function called ABS, then this is what it would look like. It would have a name, it would have a braces, and then have a return type and the execution statements. This is a typical function declaration. But a method is different from a function in a way that before the name of the function, we have the receiver. This part is called the receiver. And this type, and whichever type this matches, then we will say that we are defining a method called ABS on the type vertex, because in the receiver, we have the type vertex. That's how we assign a method to a type. That's about the syntax. And then we have here available V, which is of type vertex, which is a struct. And this is an instance of the struct, not the type itself, but a concrete instance of the struct. And usually we write a short variable because we'll again and again have to access that. But you can make it readable also. It is not that important. And along the way. Now we have a very interesting concept called interfaces. And interfaces are something that is very deep into Go's philosophy. And you'll find interfaces everywhere in the standard library, in all the packages. And it's a very important concept to understand. And for now, as long as you understand the basics of it, even if you don't understand completely, it's fine. And we'll use interfaces in our projects. And when we are reading code, we'll look at a lot of interfaces and we'll see how they work. So for now, let's just understand the basics and move on. Let's not spend a lot of time here, because interfaces can be a little tricky to understand in the first look, and you get the feel of it as you work with it more and more. Okay. So let's understand what's happening here. For now, we have a type here, and it is not any other type. It is not a struct or integer or string or anything. It is of type interface. Now, what goes inside the interface type? Inside the interface type, we have methods. We have method signatures. That's all there is to it, to interfaces. We have interfaces, and inside that, we have method signatures. Now, how do they work? How are they useful? To understand that, let's dive into the example. Here, we are declaring a variable of type interface, of type this appser interface. We have a variable, and it's called to be implementing stringer, as long
we're going to be talking about interfaces. Now, interfaces are very important and very powerful inside of Golang, and in fact, inside of any real typed language. If you're coming from a more dynamic language like JavaScript or Python, you've probably never heard of an interface, and in fact, you don't really need to use one in those languages. I mean, I suppose you could, but there's not really a real good purpose for it, whereas in a language like Golang, it makes a lot of sense. Now, what is an interface? Well, an interface is really a way of looking at a set of related objects or types. So let's have a look at this example here to really explain this. We have a circle and we have a rectangle, and they both have this similar behavior in that we can call area on them. I can call a rect area, I can call a circle area, and they both have a different implementation, but they both have an area. So in theory, the rectangle and the circle could be looked at in the lens of they both have an area. They're both of shape. They both have some kind of area. I don't need to know anything more about them other than that they have this area, and well, I should be able to use that area on them. That's kind of what I'm getting at with the interface. The interface lets you look at these types as if they're the same. It kind of hides the details underneath and says, we just care about the fact that these both have area, or they both have a perimeter, or they both have something, right? That's what interface lets us do. It lets us define some kind of behavior that is similar between objects or similar between types so that we can use these types kind of one and the same with their related behavior. Now, a good example of this is if we wanted to make a slice, for example, of C1 and R1. So maybe I want to do this. I want to say shapes, equals, and I want to make a slice. We want it to be some type. I don't know what the type is, so I'm just going to write type for now. And then we want C1, R1. Now, of course, we don't know what to put here. And this is going to be an error, right? We need to put some kind of type when we define this slice. But what type do we put here? We have no idea, right? Now, what I want to do, though, is I want to look through shapes, and I want to call area on both of the shapes. I want to be able to do something like shapes0.area and shapes1.area. And in fact, if we look, we assume that this is valid. It's not, but assume it's valid. Then really this should work, right? Because both the circle and the rectangle have this area method. So I should be able to do shapes0.area and shapes1.area. And that means that maybe if I had a huge slice of shapes, I could do a for loop and loop through them and call .area on all of the shapes and sum up the area, right? Or something like that. But right now we can't do that. And this is where an interface comes in. It lets us do exactly the behavior I'm trying to illustrate to you. So I'm just going to define an interface, and then we'll talk about it more in depth. So I'm going to define type, shape, interface like that. And inside of here, I'm going to say area, float 64. Oh, not inside the brackets. Put it there. All right. So what I've done now is I've defined a shape interface. And all this says, the whole point of this interface is really just to say that anything, any type, any struct that has this area method that returns float 64 is of type shape. It implements the interface shape. So we say that when some kind of struct, so one of these types that we've defined, has right in here and save, and this is totally fine. What does it say here? Shapes declared and not used. Yeah, so that's a common error. That's not.
Now, finally, we reach concurrency. One of the strong points, one of the strong selling points of the language Go. And there is a lot to say and there is a lot to understand in this topic. And as I said in the initial part of this video, this is one of those topics in the language where if you're a beginner, you should not try to understand everything. If you do that, that will only intimidate you. Of course, if you get all the concepts and if you're comfortable with all the concepts that Go has to offer in this topic, then that's fine. Then that's great. But if you don't get it, then that's also fine. If you get some of it, then that's fine. If you don't get any of it, then that's also fine. We'll explore more and more resources later on in this series, and eventually you'll get it. Eventually you'll get the hang of all the constructs that Go has to offer in this area. Okay, with that, let's jump into this example. of Go routines. Now, what's happening here? We have a function called say, and it is taking one string. It is taking one string and it has a for loop. Inside the loop, it is looping 5 times from starting from 0 to 4. And in each iteration, it is blocking the execution. Time.sleep blocks the execution and it is blocking for 100 milliseconds. We have a constant called time.millisecond for each millisecond, and we are blocking for 100 milliseconds in each iteration. And after blocking for 100 milliseconds, we are printing that string, whatever string that has been passed to this function. Now it happens 5 times. For each function call, it happens 5 times. Okay, now what's happening in the main function? In the first line, we have this function. We are calling this function, but before that, we are adding this prefix called go. And then in the next line, we are calling this function normally. Now, what does this go do? This syntax, go and then calling a function, this actually spawns a new go routine which runs concurrently, with the main go routine. Now, there are some concepts to understand here. In every Go program execution, whenever we are running a main a new go routine is created. Is called the main. It's called the main go routine, and everything that gets executed sequentially that happens in the main go routine. So this part, the say hello, the normal function call, and all the examples that we've been seeing so far, all of them have been executing in the main go routine. Now, Go provides us this construct called Go routines. Then what is a Go routine? Go routine is basically similar to a thread that are offered by other programming languages, but it is very different from a thread. To wrap your head around the concept, you can think of it as a thread, but Go routine is something that is managed by the Go scheduler. It is managed by the Go scheduler. It is not managed by the operating system. Now, that's one thing that is a difference between a Go routine and a concrete operating system thread that is offered by other languages. Number one, they are not managed by the operating system. They are managed by the Go scheduler. The Go runtime. Go has a dedicated component which is called a scheduler, and that manages all the scheduling and running of Go routines, the blocking of Go routines and everything. Number one difference is Go routine is managed by the scheduler. Second, one of the advantages of using Go and using concurrency primitives in Go is Go routines are very lightweight. Very lightweight. And what do you mean by lightweight? Typically, when we spawn threads in other programming languages, which are operating system threads, threads are pretty heavy. A typical thread depends. depending on the implementation, depending on the language, they might range from a 256 KB to 1 MB of memory in stack. Now each thread takes up this amount of memory. Now, on a high level, this might not seem a lot, but when you spawn a lot of threads, then it can cause your system to run out of memory, and it can cause memory leaks and a lot of problems if you are not managing your concurrency workflows efficiently. Now, Go routines, which are provided by the Go runtime, they are advantageous in this scenario because they are very lightweight. A typical Go routine has a size between 2 KB to 4 KB, a starting size, and they are dynamically resized, which means they are not fixed depending on the requirements of the Go routine, depending on the memory requirements, the allocation requirements of the Go routines. They can resize themselves up to whatever size they need, from hundreds of MBs to GBs, depending on the system requirements, until the system runs out of memory. Now, that is the second advantage. Go routines are very lightweight, and Go routines are managed by the Go scheduler instead of the operating system. Those are 2 points. Now, that's about Go routines. But why do we need Go routines in the first place? Go routines are the Go's way of providing concurrency features. Now, what do we mean by concurrency? Now, a lot of languages provide concurrency in their own way. JavaScript provides concurrency using the construct of event loop. And different languages have different implementation of the concept concurrency. So what do we mean by concurrency in the first place? Concurrency is basically managing execution of different tasks efficiently so that it does not block the system flow. Now, that is a very abstract definition of concurrency. Different tasks efficiently. Basically, managing execution of different tasks efficiently so that it execution of different tasks efficiently so that it does not block the system flow. Now, that is a very abstract definition of concurrency. Now, whenever we talk about concurrency, a different topic also comes into discussion, which is called parallelism. There are a lot of resources. There is a lot of debate surrounding the difference between concurrency and parallelism. And you can explore that to understand the concepts that surround them. But on a very high level, parallelism is a hardware feature we can imagine, and concurrency is a software feature. It is something that is provided by your language, your software, your system, is an operating system, whatever. And parallelism mostly depends on your hardware, depends on your CPU cores. How many CPU cores do you have? Because concurrency is executing tasks in the most efficient order. to have the minimum amount of latency, to not waste resources of CPU, to not waste resources of memory. Okay? Concurrency does not mean that two tasks are being executed parallelly. Okay? Concurrency basically means if you have, let's say, 4 tasks all spawned at the same time, then depending on your system's implementation and depending on your language handling capabilities, those 4 tasks might get executed in any order. The order is not specified when we are talking about concurrency. Now, these 4 tasks can be executed in any order. The first, the second, the fourth, then the second, then third. At a time, one task might be executing, and if your system supports parallelism, then at a time 2 tasks or 3 tasks might be executing. But that is completely different from concurrency. Concurrency is basically executing your tasks in a most efficient order. The order is not specified. It depends on your implementation. It depends on the programming language. But parallelism is truly executing tasks in parallel. Like both tasks are getting executed in parallel in your CPU cores. Okay, that's basically a high-level introduction of concurrency versus parallelism. And now, as I said, there are a lot of resources that you should explore. A lot of resources in YouTube, for example, very good talks by Rob Pike, one of the co-founders of the Go programming language, and a lot of other resources that you should definitely explore. I don't have the capability and definitely don't have the time to get too deep into the concurrency philosophies and the parallelism versus concurrency debate. So this definition should be enough. Now, circling back to where we started from, Go routines are Go's way of providing concurrency features to the users of the language. Now, Go routine is the primary component which provides the capability of concurrency. And the thing to remember is every Go program execution starts with the main Go routine, and other Go routines are spawned from the main Go routine. And the moment the main Go routine returns, the moment the main function returns, all the Go routines are abandoned and they will be collected by the garbage collector and all. But you won't see the execution, the results, whatever you are expecting from them, because as long as the main Go routine is running, all the other Go routines are executing in concurrently with the main Go routine. So you can imagine it as this is the main Go routine, and this is the execution flow. of main. And during the execution, we can spawn different coroutines from main. For example, we spawned 2 coroutines here from main. Okay. And those coroutines can spawn more coroutines during their life cycle. And it can go on and on. But at the end, the main coroutine has to wait for all these coroutines to finish. Otherwise, you won't see the results. You won't see whatever results that you are expecting from these executions. Even though these coroutines are running concurrently with the main coroutine, they cannot run independently outside of the main coroutine. They depend on the main coroutine to wait for them. That's something to remember. Now, with that basics, now we can jump into the example of what's happening here. We have a function and we have the syntax called go. And whenever we call a function with this syntax go, this language spawns a new go routine which executes concurrently with the main go routine. Now, when we run this example, this is what we see. Now, the other thing to remember is once you spawn a go routine, there is no guarantee. There is no way to know for sure that if this go routine started executing immediately or if the next instruction, whatever the instruction in the main go routine executed at that point of time. You cannot say. The moment you spawned a go routine, there is no way to know for sure that which statement executed first. Now, we can just imagine to distinguish between those two. In the go routine that spawned from the main one, we are saying we are printing world. We are printing world 5 times with a blocking time of 100 milliseconds between each iteration. And in the main go routine, we are printing hello 5 times with a blocking time of 100 milliseconds with each iteration. Now, if you look at the results, this is what we find. First, we see world, which means the moment we spawned this go routine, it started executing immediately after the 100 millisecond blocker. Then we see world, then we see hello, then we see world, then we see hello, then we see world, then we see hello. So if you look at it, there is no specific order. As I mentioned, concurrency means the order is not specified. It depends on your implementation and it depends on your language. Now, Go promotes this philosophy, CSP, communicating sequential processes, which basically states that, which is very different from how other programming languages sequential processes, which basically states that now Go promotes this philosophy, CSP, communicating sequential processes. Which basically states that, which is very different from how other programming languages approach concurrency, which is basically by sharing state. Now, Go promotes a different philosophy, which states that don't communicate by sharing memory, share memory using communication, which is a very abstract way of saying instead of using shared memory or shared state to implement concurrency, you should depend on communication between different threads, or in this case, communication between different Go routines to implement concurrency. Do not share memory, because sharing memory for historical reasons, from historical evidences, we have experienced that sharing memory or sharing state gives birth to a lot of problems. If you you are not someone who is expert at implementing concurrency primitives. Problems like starvation, problems like deadlock, and all these problems can be avoided using communication as the means of concurrency implementation. Now, all of those problems do not just go away, but the philosophy, the mindset of sharing state using communication can prevent a lot of those bugs. It does not prevent all of them, but the way they are structured, the way they are implemented, the way they promote people to use it, they can avoid a lot of those bugs. There is a very small room for making classical or historical mistakes when it comes to concurrency. That's why Go has this primitive, Go has this construct called channels. And channels are, in one line, channels are data types. They are data types which allow two Go routines to communicate with each other, which allow two Go routines to send data to each other. That's a very revolutionary idea, and you can do your own research to study all the materials surrounding it. But there is a very small room for making classical or historical mistakes when it comes to concurrency. That's why Go has this primitive, Go has this construct called channels. And channels are in one line, channels are data types. They are data types which allow two Go routines to communicate with each other, which allow two Go routines to send. Send data to each other. That's a very revolutionary idea, and you can do your own research to study all the materials surrounding it. But that's the philosophy behind it. Instead of sharing state, instead of implementing mutual exclusion, Go also has construct for classical implementation of concurrency for like concepts like mutual exclusion and mutexes and semaphores and all. But Go promotes heavily the idea of channels. And the idea of channels are, in most of your concurrency-based implementation, try to see if you can solve the problem using channels. Which basically means try to see if you can solve the problem using communication between two Go routines. Instead of using primitives like semaphores and mutexes, try using communication as your first approach to solving concurrency-based problems. That's why we have channels, which are basically data types, so that two Go routines can communicate between each other. Now, that's what's happening in this example. Let's explore this. We have a function called sum, which takes a slice of integers called s. In the second parameter, we have a variable called c, which is of type channel, and it is a channel of integer, which means a channel is basically one hierarchy above other data types. So a channel can be thought of as a container. Channel itself is not a data type. Channel can be thought of as a container data type, and you have to specify what kind of data goes inside the channel. So if we think about channels, if you think of channels as these tunnels, we have one Go routine and we have other Go routine, and we want to send data. Okay? We want to send data. Data might be this side, that might be this side. And this data, we have to specify what kind of data goes in these channels. So it can be integer, it can be string, it can be any kind of Go data type. So a channel has to specify what kind of data goes inside the tunnel, what kind of data Go routines will send each other. That's what we have this integer. This basically says this is a channel which will have integers inside it, which basically Go routines will send integers using this channel, using this tunnel. Now, inside this function, we are declaring a variable called sum, and then we are ranging over this provided slice, this slice of integers, and we are basically calculating the sum and storing it here. Then after we are done, we are sending the result into this channel. As I said, channels can be thought of as a tunnel where we will send data. two coroutines will send data to each other using a channel. That's why after we have this result, we are sending our data through this channel or this tunnel. You can imagine channels as tunnels. You are sending the result into this channel. Now, another thing is that we and channels this trying to find the sum of the first half, and in the second function call, we are trying to find the sum of the second half. We are spawning these two coroutines. Now, now this is the important part. We spawn two coroutines and we pass this channel, we pass this tunnel, we pass this data type using which those coroutines can send data to our main coroutine. As I said that main itself is a coroutine and all the coroutines are spawned from main. And since we know that channels are a means of communication between two coroutines, what we can do, we can spawn different coroutines from main and we can use channels to send data, to send signals to our main coroutine, to our main execution. And that's what we are doing here. We created a channel which is of type integers, which basically means we can only send integers to this channel. And we spawn two coroutines, which call two functions, which are running concurrently with the main function. Now, in this line, what we are doing, we are declaring two variables, x and y, which is a short form declaration. And we are receiving data. We are again using this syntax. We are receiving data from two. And if you run this, we are getting the sum of the first half.
Oh.
And then we are getting the sum of the second half, and then we are getting the result of x plus y, basically the sum of all elements. Now, what are we trying to do here? First thing, we are trying to divide our work. We are trying to divide our work between two coroutines. If we just call the sum function without spawning a new coroutine, we just call the sum function in the main coroutine. If we did that, then it will just go through all the elements and give us the sum. Now, since we know using concurrency, we can divide our work as long as the order is not specified. That's the important thing to remember. As long as the order is not specified, we can divide our work using concurrency. And we have Go routines to implement concurrency. That's the reason we spawned two Go routines and we divided our work. We called the first Go routine with half of the elements and the second Go routine with half of the elements. then this is the important part. We waited, as I mentioned earlier. If the main go routine does not wait for all the go routines that were spawned from the main go routine, then the execution will stop. Then we will never find the result. So channels, receiving from a channel is a blocking execution. You should remember this. Receiving from a channel is a blocking execution. And since we try to receive here, twice, then we got the value of the first go routine, which tried to send some value into this channel. And then we got the value of the second go routine, which tried to send some value into this channel. And we received twice from this same channel. And that's the reason the main go routine did not end. The main go routine waited for these two go routines to end because of these channels. So now everything comes together. We have go routines. We have go routines to spawn, to divide our work, to have the capability of concurrency. And we have channels. We have channels to synchronize or to orchestrate or to communicate between these go routines, whatever you can imagine. There are a lot of use cases of channels. There are a lot of implementation, a lot of starting from basic to very complex implementation. And this is a very simple example of using channels to orchestrate different go routines because of the property that in the main go routine, as long as you're receiving from a channel, it will block. Now we have two types of channels. One is called a unbuffered channel and the second one is buffered channel. And the high level difference between these two are a buffered channel acts like a queue. We have a queue here. And if we have a buffered channel, and we have a go routine. So the go routine can push values into this buffer or a queue. Let's say this size of this buffer is 4. So this go routine can keep pushing into this queue until the size is filled. So it can push 1, it can push 2, it can push 3, and it can push 4. And until the buffer is full, this go routine, whatever go routine it is, it can keep pushing into this channel. And it won't block. It won't have to block the execution. And on the other side, if there is another go routine which is receiving from this end, which is receiving from this same channel, then the whole workflow will go in a very nice way. Because the producer, we can think of this go routine as a producer and this one as a consumer. The producer can produce at its own pace. It won't have to wait for the consumer to take out the data. It can keep pushing and the consumer can consume at its own rate. So there are no blockers here until the buffer is full. But in a unbuffered channel, we don't have a queue. We just have a tunnel. There is one go routine, is the producer, and there is another go routine, is the consumer. And this interaction will block. Let's say this go routine has a value to send, which is called 1. This is the value it wants to send. So until this receiving go routine takes this value, until both of these are in sync, until this tunnel is synchronizing, this interaction will block. So on a high level, as you can see, buffered channel has a little flexibility. And whenever we have a producer and consumer based scenario, then the pace of producing, the pace of sending is different to the pace of receiving or the pace of consuming. Then we can go with a buffer channel. Or if we know the maximum size of this channel, if we previously know what is the maximum size of this channel going to be, how many values that we will be needing in future. In those cases, we can go with a buffer channel. And since we have the construct of make, which provides some kind of capacity during initialization, as we saw with slices, as we saw with maps, in the same way, using make, we can assign a predefined capacity to a channel, and that channel will be a buffer channel. It will have a queue. It will have some kind of storage mechanism so that the interaction does not block. That does not mean that we should always use buffer channels. Sometimes we also need unbuffered channels, which causes the interaction to block. And because the interaction is blocked, unbuffered channels are mostly used for synchronizing. When the property of synchronization between two go routines are of utmost importance, or if we need the property of synchronization, if we need the property of blocking, then that's the scenario. We go with unbuffered channels. We don't want any queue. We don't want any buckets. We don't want any storage mechanisms. We just want to synchronize two go routines. On a high level, those are two different use cases of unbuffered channels and buffered channels. And in this example, what's happening? We are creating a channel which has a capacity of 2, and we are using the make function to create this channel. And this 2 is basically the size of our queue. It can maximum push 2 elements, and until the buffer is full, until it has 2 elements, we can keep pushing to it. And that's what we are doing here. We are pushing the first value, we are pushing the second value into the channel. And in the print statement, we are waiting for this value. Yeah. And if you try to run this example, we get 1, 2 as expected, nothing special. We just explored this example to look at the two different types of channels. One is unbuffered channel, the second is buffered channel. Now, in this example, we have a couple of new concepts. We can see there is one, we are using close. The second one, we have a range. Instead of ranging over a string, instead of ranging over a slice, we are ranging over a channel. Now, what's happening here? So we have some notion about go routines and channels and the main go routine blocking and all. A couple of properties to keep in mind while we explore this example is, first one, main go routine has to wait until all the go routines are finished executing, until all the values are received from the channel. Basically, main go routine has to wait. Otherwise, the go routines that has been spawned from the main go routine, they will never finish executing. That's the first thing. Second, we already know that channels are used to communicate between two go routines. They are some kind of tunnels to communicate between two go routines. Now, in some scenarios, you might ask the question, if two coroutines are communicating, one is sending, one is receiving, or other one is receiving, other one is sending, in those scenarios, how will the other coroutine know that the sending has been finished, or when will it stop receiving, when to stop waiting for values in this channel? That's the reason we have this function called close, and this function is a predefined function provided by the Go runtime, which is used to send a broadcast signal to inform the parent Go routine that the sending has been finished. We don't have any more values to send in this channel, so that you can stop receiving, you can stop blocking the execution. Those are the two concepts that we will focus in this example. Now what's happening here? We have a function which calculates the Fibonacci series. And it takes one integer and it calculates the Fibonacci series up to that integer. We already know what is the Fibonacci series. We basically have this series 0, 1, and you add these two numbers, you have 1, and you add these two numbers, you have 2, you add these two, 3, then 5, then 8, then 13. This is basically a Fibonacci series. It's a mathematics concept, and that's all you need to know. What is a Fibonacci series? What's happening here? This function basically calculates the Fibonacci series. It declares two variables x and y. They start with 0 and 1, and it loops until the number n, whatever you provided. How much to extend the series? That is basically the number n. It loops until that number, and in each iteration it sends the current value. Basically first it will send 0, then 1, then 1, then 2, then 3, then 5, then 8, then 13. It will send all these numbers in the Fibonacci series one by one into this channel. That's what it's doing overall. But in the end it is calling close. So let's say we have provided the number 4 in n. What will happen in the first iteration? The I will be 0 and it will send the value of I to this channel. So we have this channel, and this channel has the capacity of 10. It has the capacity of 10, so it can maximum hold 10 values at a time. As long as there is a receiver taking values out of limit, it can hold any amount of value. But at a time, maximum amount of value without any receiver taking out values from it, it can hold 10 values. The capacity is 10. Now, in the first iteration, it sends 0. It has 0. Then in the second iteration, I has 1. Then it sends 1. Then in the next iteration, 1, then 2, etc., etc. This is how it works. In the end, since our value of n is 4, and maximum it will run 0, 1, 2, 3, 4 times. It will run 4 times. After it is done, after this for loop ends, it calls close. Now, the reason we need this close is because after this loop ends, we want to inform the channel. We want to inform the main go routine. block. Very complex implementation. And if we have a buffer channel and we have a go routine, so the go routine can sequentially, the go routine can push values into this buffer or a queue. Let's say this size of this buffer is 4. So this go routine can keep pushing into this queue until the size is filled. So it can push 1, it can push 2, it can push 3, and it can push 4. And until the buffer is full, this go routine, whatever go routine it is, it can keep pushing into this channel and it won't block. It won't have to block the execution. And on the other side, if there is another go routine which is receiving from this end, which is receiving from the same channel, then the whole workflow will go in a very nice way, because the producer, we can think of this go routine as a producer and this one as a consumer. The producer can produce at its own pace. It won't have to wait for the consumer to take out the data. It can keep pushing and the consumer can consume it at its own rate. So there are no blockers here until the buffer is full. But in a unbuffered channel, we don't have a queue. We just have a tunnel. We just have a tunnel. There is one go routine, which is the producer, and there is another go routine, which is the consumer. And this interaction will block. Let's say this go routine has a value to send, which is called 1. This is the value it wants to send. So until this receiving go routine takes this value, until both of these are in sync, until this tunnel is synchronizing, this interaction will block. So on a high level, as you can see, buffered channel has a little flexibility. And whenever we have a producer and consumer based scenario, then the pace of producing, the pace of sending is different to the pace of receiving or the pace of consuming. Then we can go with a buffer channel. Or if we know the maximum size of this channel, if we previously know what is the maximum size of this channel going to be, how many values that we will be needing in future, in those cases, we can go with a buffer channel. And since we have the construct of make, which provides some kind of capacity during initialization, as we saw with slices, as we saw with maps, in the same way, using make, we can assign a predefined capacity to a channel, and that channel will be a buffer channel. It will have a queue. It will have some kind of storage mechanism so that the interaction does not block. That does not mean that we should always use buffer channels. Sometimes we also need unbuffered channels, which causes the interaction to block. And because the interaction is blocked, unbuffered channels are mostly used for synchronizing. Because the interaction is blocked, unbuffered channels are mostly used for in the same way. In those cases, we can go with a buffer channel, and size is different to the pace of receiving or the pace of consuming. Then we can go with a buffer channel. Or if we know the maximum size of this channel, if we previously know what is the maximum size with slices, as we saw with maps, in the same way, using make, we can assign a predefined capacity to a channel, and that channel will be a buffer channel. It will have a queue. It will have some kind of storage mechanism so that the interaction does not block. That does not mean that we should always use buffer channels. Sometimes we also need unbuffered channels, which causes the interaction to block. And because the interaction is blocked, unbuffered channels are mostly used for synchronizing. When the property of synchronization between two go routines are of utmost importance, or if we need the property of synchronization, if we need the property of blocking, then that's the scenario we go with unbuffered channels. We don't want any queue, we don't want any buckets, we don't want any storage mechanisms, we just want to synchronize two go routines. On a high level, those are two different use cases of unbuffered channels and buffer channels. And in this example, what's happening? We are creating a channel which has a capacity of 2, and we are using the make function to create this channel. And this 2 is basically the size of our queue. We can maximum push 2 elements, and until the buffer is full, until it has 2 elements, and main go routine has 10. Now, what's happening here? So we have some notion about go routines and channels and the main go routine blocking and all. Couple of properties to keep in mind while we explore this example is, first one, main go routine has to wait until all the go routines are finished executing, until all the values are received from the channel. Basically, main go routine has to wait. Otherwise, the go routines that has been spawned from the main go routine, they will never finish executing. That's the first thing. Second, we already know that channels are used to communicate between two go routines. They are some kind of tunnels to communicate between two go routines. Now, in some scenarios, you might ask the question, if two go routines are communicating, one is sending, one is receiving, or other one is receiving, other one is sending. In those scenarios, how will the other go routine know that the sending has been finished, or when will it stop receiving, when to stop waiting for values in this channel? That's the reason we have this function. function called close. And this function is a predefined function provided by the Go runtime, which is used to send a broadcast signal to inform the parent Go routine that the sending has been finished. We don't have any more, though we already know what is the one into this channel. That's what it's doing overall. But in the end, it is calling close. So at a time, when we ranging over a channel. Now in Go, you can range over a channel. You then takes back calls. What happens that are receiving values from this channel that we have stopped sending values. Fibonacci again, and it is taking two channels. One channel called C and another called quit. And both are channels of type integers. We can only think, as I said, if, as we have discussed before, if inside a for loop we do not have a condition, then it is by default an infinite loop. Now there is nothing to worry here. As I said initially during the start of the video when we were discussing for loop, there are uses of here. And what's happening inside the infinite loop, which this infinite loop basically means this will not stop executing until there is an explicit return or an explicit break. And we have a return in this called C. And inside that, what this basically means, if this is successful, if we can send it, then this gets a quick as we reasons, where else run anonymous functions, and it loops for it 10 times. Which routines we are sending the value of X with checks are C is an unwing 10. Quit little how everything is working. You just have to understand the concept that we have a select block and we can orchestrate channels using selects. So we are just going through concepts. You don't have to master concurrency at this phase. Okay. Now both of these are being run at the same time, and the moment this receive the loop breaks, the main Go routine, all the Go routine stop each iteration. We are receiving the value of X into this, and we are printing it. Done, and this loop broke, and how they work in the concurrency space. Now, for us to understand how select works in a much deeper way, in a little deeper way, we have another example. What's happening here is functions select case channel. We reach the default case where we print 100 milliseconds more to wait until there is done is the end of the. Here we have a struct. Inside the struct we have a field called v, which is of type map, and in this the key string and the value is integer. And this struct has two methods. One is increment and one is value. Increment basically mutates the value of the map and returns struct with make this is a group set, but we'll cover them later. We should ideally use a channel or a main map. Now what happens? How can we fix this? For this, in this area, which is should ideally use a channel or a wait group to block the main function. But for the sake of this example, we are using time.sleep to block the execution of the main Go routine so that we can see the results of all these 1000 Go routines. And in the end, we are fetching the value of this key from this map. Now, ideally, what should happen? 1000 Go routines are spawned, and all of them are incrementing the value of this key. So ideally, it should start from 0, and by the end, it should have the value 1000 because we spawned 1000 Go routines, and each Go routine incremented the value by 1. Ideally, we should have 1000. But what happens if we run this? When we run this, we get this error. And when we go to the top, it says concurrent map writes. And what that means is we spawn 1000 Go routines, and all the Go routines are trying to access it. They are trying to write a value to this map in an unspecified order. And because of that, Go was able to detect that there is a problem in this program. When you are working in the space of concurrency, you have to constantly think about orchestrating state between your Go routines. So this is a classic example of that. You have different Go routines, in this case 1000 Go routines, and all of them are trying to mutate a value in an unspecified order. And to prevent this case, to prevent this exact scenario, we have a construct which are called mutex. Mutex basically, it's a concept from operating system if you have studied. Mutex, what they do, they are basically gatekeepers. They keep the gate, they have an entry point and an exit point. And whatever happens in this area, which is called mutual exclusion area, whatever happens, this is safe from concurrent access, so that only one Go routine at a time can access this area. It does not matter how many Go routines you have. In this case, we have 1000 Go routines. Even if you have million Go routines at a time, only one Go routine can access this area. Okay? And the moment it unlocks, at this point it locks, and this point it unlocks. After it unlocks, another Go routine can acquire this lock, and it can do something, and it can then unlock. And with this flow, now we are safe from multiple Go routines, all of them trying to concurrently mutate the value of a map. Now what happens? How can we fix this? For this exact use case, Go provides us this package called sync, and inside this sync, we have this value called mutex. Now, inside the same struct, we add this another field called mutex. And now what we do, in the increment method, we lock it. At the start of the execution, we lock it. And we mutate the value. After you mutate the value, we unlock it. So that this is the mutual exclusion area. At a time, only one Go routine can get inside this area. And at a time, only one Go routine can, after that Go routine unlocks it, another Go routine can acquire the lock, and it can mutate this. In the same way, if we have the value function and this value function acquires the lock and it defers the unlock function, as you already know, we use defer in different scenarios so that ends Go will automatically call this function because we added defer here. That's what we are doing here. We are acquiring the lock and we are saying before this function returns, unlock it. So we are not exclusively guarding what the area is. We are just saying we want Fusion area, what it is doing. It is getting the value for that key. Okay. Now we have concurrency safe mutation and concurrency safe access for this map. What happens when we run this now? Let's run this. And as you can see, we have our expected result of 1000. We can guard the access of Go, all the examples of the tour of Go with the end of concurrency.